We now know that an integer exponent means repeated multiplication. So for instance, if we have an expression such as 5 to the third, we know that that means 5 times 5 times 5. And if we have an expression like x to the fourth, we know that that means the same thing as x times x times x times x. But what might it mean if we had an expression such as 4 to the 0 power? You could make an argument that, well, maybe that should equal 0, or maybe that should equal something else. But when mathematicians try to figure out the meaning of something new, what they want to be sure of is that all of the previous patterns and all of the previous methods of working with exponents still apply. So let's think of one of the patterns, at least, that we know applies. Well, when we're simplifying an expression such as 5 squared times 5 cubed, we know that we can simplify that by simply adding the exponents and make that 5 to the fifth. X to the fourth times x to the 12th, well, we don't have to write out all of those x's. We can just figure out that this is x to the 4 plus 12, which equals x to the 16th. Now with zero exponents, let's see what patterns exist and see if we can fit a meaning into those patterns. So let's start with equations, and let's just try to solve them without exponents. So first of all, let's think about 2 squared times what equals 2 squared. Well, this is 4 times what equals 4. So what makes sense is that this equals 1. Let's take another problem. 5 to the third times whatever equals 5 to the third. And again, what makes sense here is 1. And we'll do one more. 6 to the 100 power times what equals 6 to the 100 power. And of course, 1 would be the best answer. Now, let's write these as exponential equations and see if we can see what makes sense. So 2 to the 2 squared times 2 to the what should equal 2 squared. Well, we found earlier that adding the exponents is one way of simplifying. So this should be 2 squared times 2 to the 0 equals 2 squared. And if we look at these two equations, we see that it makes sense for 2 to the 0 to equal 1. Let's try that with 5 to the third. 5 to the third times 5 to the 0 should equal 5 to the third. 3 plus 0 is 3. That makes sense. And that means that 5 to the 0 should equal 1 as well. And the same thing with 6 to the 100 times 6 to the something equals 6 to the 100. If the previous pattern holds, 0 is what makes sense. And looking at this previous equation, we see that making 6 to the 0 equal to 1 makes sense. So we can take a guess that anything to the 0 power would equal 1. Now there are some other patterns to consider. So let's take a look at another pattern. If we started with 16, 8, 4, 2, what would be the logical next choice? Well, if you consider what the pattern is, we start with 16 and keep dividing by 2. So 16 divided by 2 is 8. 8 divided by 2 is 4. 4 divided by 2 is 2, and 2 divided by 2 equals 1. So that makes sense. Now let's take a look at these in exponential notation. 16 is 2 to the 4th, 8 is 2 to the 3rd, 4 is 2 squared, 2 is 2 to the 1st. So what logically comes next? Well, 2 to the 0 comes next, and that should equal 1 as well. Each time we move in this direction, we are also dividing by 2. So it makes sense in these two contexts for anything to the 0 power to equal 1. And in fact, that's what mathematicians have agreed on. This applies to really large numbers, so 1 million to the 0 power equals 1. And it also applies to variables. So if we have a really complicated expression like x cubed times 2y squared z to the 4th to the 5th over xyz, and all that to the 0 power, even that equals 1.